No? Is it Lumos? Try it. Standard position. Standard position is when we sketch angles called rotational angles on the Cartesian plane, the x, y axis, with the initial arm where the angle starts as the positive x-axis always. These angles can be positive. If you move counterclockwise and negative, you move, if they're positive, they move counterclockwise. If they're negative, they may move clockwise. And that's reviewed from 20-1 possibly. Maybe not. Who cares? Positive rotational angles. So we're going to have an x and a y axis. Boom. Let's draw it. And then boom. Let's draw it. Okay. So we're going to do positive rotational angles, which means we move counterclockwise. No matter if it's positive or negative, we start on the x-axis, the positive x-arm. So I'm going to do degrees first, because we're going to do radians a little bit. So this is 0 degrees. Then this would be 90 degrees, because it would make the little box, right? Then another 90 is 180. Then another 90 is 270. Another 90 is 360. And then in 20-1, that's actually the 20-1 curriculum is from 0 to 360. That's it. So if you did any more or any like negatives or going to like 480 or anything, you actually did more. So well. So I kept going positive and I kept going negative with my normal class anyways, but it doesn't matter because that's not the hard part of trig, whether you did that or not. So you would keep going if you wanted to. So it'd be 360, then it would be what?
450.
Yes. Then it would be 540 because it's just dropping by 10, right? Then it would be 630. Then it would be 720, and it would keep going, correct? On for life. Now, the key thing about drawing angles is your initial arm has to be on the x-axis and it has to rotate about 0, 0. So I'm going to use red. So I would have my 0, 0s here. This has to be my initial arm. It has to be on the x-axis and it has to have an arrow because it's an arm. So I'm going to write this. You don't have to write this each time. I'm just showing you. This is the initial arm. Now say I'm drawing 120 degrees, correct? I'm going to draw a circle because it's rotating, and 120 is either 60 less than 180 or 30 more than 90, correct? And remember, if it's 90, it's 30, 30, 30. It's broken into thirds. If it used 30s, it's 45. That would break it in half. So you can do like if it's 120 and you draw it close to the x-axis, you're not right. If it's 120 and you're like drawing like it, and I brought out a protractor and it was at 123, we're going to call it good. Okay, like I'm not bringing out a protractor to check it. However, if you like draw it here, like close to the 180, and you're like, oh, 120. No, it's not. That's like 170. You were way off. Okay, so it's about 30 more than 90. So I'm going to go draw it here, let's say, about a third of the way. So that's going to be my terminal arm. Once again, you don't have to label these all the time. I'm just showing you what they're called. Now, this is the catch. If you didn't do this before, you will have to do this now. You have to draw an arrow from the initial arm to the terminal arm. And if the arm is going counterclockwise, it's a what? A positive angle. We agree? So that's why this is 120. Because you're borderline geniuses, can anyone guess what the negative rotational angle that would end on that same arm is? Yeah.
It's just 360 minus 120.
Which is?
240.
Yeah, negative 240. Because it's just, this is a full circle, correct? It's 360. And what I want to do is I want to head this way. So this would be negative 360 to get me to that arm. So instead of doing a whole 360, if I subtract the 120 off, I'll get what the negative rotational would be. See? You know more than you. All right. So we're going to draw this. Always label your axis. I know it takes time, but I promise you, you'll make less mistakes. 0, negative 90, negative 180, negative 270, negative 360, and it would keep going. Now, if I still draw my rotation, it rotates there. It's still my initial arm. This will still be my terminal arm, but I told you we're going to go clockwise this time. So it's negative 90, negative 180, negative 240. So you label it as negative 240, but you also show, you see how it shows the arrows going clockwise to tell you that it is actually a negative angle. These are called coterminal angles. So 120 and negative 240 are coterminal angles because they terminate on the exact same spot in the graph. Now let's think about the unit circle to kind of remember what it was. The unit circle had angles on it, and then it had coordinates around the outside, correct? And the coordinates actually were, that coordinate that you wrote on the outside was actually the coordinate for that dot on the outside of the unit circle. The unit circle is actually full of infinite number of dots, and the infinite number of dots get connected and it makes a line around it and you have a circle. But there are infinite number of dots that go around the unit circle. There's a dot at 1 degree, a dot at 2 degrees, a dot at 3 degrees, a dot at 4 degrees with a radius of 1, right? So if I drew the radius of 1, at 1 I'd have a coordinate, at 2 degrees I'd have a coordinate, at 3 degrees I'd have a coordinate, 4, 5. The ones we really wrote about were like 30, 45, 60, 90, 0, right? Those were the ones that we did with the reference angles. But there are coordinates the whole way along, correct? So there would also be a coordinate here at the very end of this arm. We agree? If this is the unit circle going around with the radius of 1. Does anyone remember what it is? Negative a half and root 3 over 2. Now, let's see if we believe them. So this one would be the exact same, wouldn't it? Terminates on the exact same dot. So this coordinate actually represents this dot in the Cartesian plane, right? With a radius of 1. Do we agree? So let's check it out. Does anyone remember the unit circle? What the formula goes for it? Is it cos then sine, sine then cos, tan, then cosine? Cos then sine. We also use Calgary stampede. So every unit circle is actually cos theta, sine theta. Calgary stampede. So we can check and see if Nathan's right. Make sure your calculator is in degree mode. This year it's going to move between degree and radian depending on if you're putting it in degree or radians, right? Now it needs to be in degree mode. I will slap my hand first. So when I go to press, now paying attention. The mode only matters if you're pressing the cos, the sine, or the tan button, correct? Or if you press second cos, second sine, second tan, that's when the degree or radian mode matters. So if you're doing polynomials and you're like, hey, Mrs. Lepp, do I have to have it in degree or radian? Doesn't matter. If you're doing logs, do I have to have it in degree or radian? Doesn't matter. Transformations, do I have to? Nope. Perms and comps. The only time it matters is if you press that button. So the moment you press cos, slap your hand and be like, what mode do I need to be in? Every single time. Be like, girl, stop. What mode do I need to be in? And how do you know what mode? The domain will either be in, restricted domain will either be in radians or degrees, or the actual question will be in degrees, right? So I slap and I'm like, oh, it's 120 degrees. I need to be in degree mode. So make sure your calculator is in degree mode and go cos 120. What do you get for cos 120? Looks as though Nathan was right. Okay, now how do I check the other one? Sine 120. And what do you get?
That's the same as
Yeah, what is it? 0 decimal?
866025403.
Right. So if you ever see 0 decimal 8660, that's root 3 over 2. If you don't trust yourself, type in root 3 divided by 2. Make sure you arrow over so the root 3 doesn't keep going over the 2, but it's root 3 enter divided by 2. And you get 0 decimal 8660, blah, 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 blah. It matches. So we know he's right, correct? We also now know the exact values of cos 120 and sine 120, don't we? The exact value of cos 120 is negative a half. The exact value of sine 120 is root 3 over 2. We also know the exact value of cos negative 240. What is it? Negative a half. And sine of negative 240 is root 3 over 2. You just answered, you could answer 4 questions right now, very quickly. Because you know the exact values. Because the unit circle immediately gives you the exact values of cos and sine of any degree. And coterminals, if we just find that that actually matches 120, we have the answers, right? All right. If the terminal arm is where the angle ends, there should be an S, and it can be in any quadrant or on any axis, right? Like it can end on 90 degrees, which would end on the positive y-axis. 180 would be on the positive x-axis. What angle corresponds to each axis label above? We already did that. So we have 0, 90, 180, 270, and then we kept going. We did the negative 0, negative 90, negative 180. I want you to sketch these 4. Go. So we're going to sketch each of the following. So if we sketch 40, we're still going to label. We go 0 degrees, 90 degrees. Trust me, if you don't have a degree, you're in trouble, because anything without a degree is a radian, and that's not what we want this to be. We want this to be degrees. 270, 360. Now, this here is at 0. Rotates around here. 45 is right up the middle, so it's a little shy. And make sure you draw your arrow this way to show that it's a positive rotational angle and say 40. Can anyone tell me what the negative coterminal would be? Yes. So whenever you're trying to find coterminals, you're going to add 360 or subtract 360, which is going to come up later in a little bit here. We're going to talk about coterminals, but why not talk about it a little early? When we see it, it's easy. Coterminals just terminate on the same arm, correct? If I need to terminate back onto this arm, I would have to rotate a full 360, right? To terminate on it, or I'd have to subtract the whole 360 to land on it, correct? Either way, if we subtract 360 or we add 360 from that angle, we'll get a whole bunch of coterminals, yeah.
So is it fair to say that every angle has an infinite number of coterminal angles?
Fair to say, yeah. So if they ask you for coterminals on a, say, diploma or on my test, I could give you multiple choice where there'd be 4, and it would have to be one that landed on there. It could be any varying level. Or if it was a written response, I could restrict the domain to ask you for the coterminals between 360 and 720, and then you could only give me 1.
Okay.
But yes, they're infinite. So how can we say that infinitely? Well, we can say the coterminal angles are 40 degrees plus 360n. And then we label n as n is an element of the integers, and I'll explain why that is in a second. So that gives actually every coterminal in the world, because there's an infinite number. Now the reason why we say 40 plus 360n, and I know we can subtract 360 and we got 320, that was what you guys just told me, negative 320 was completely correct, that was completely accurate. But if they want the general term for it, they don't give me a restricted domain, you put the n, and then you go nei, because I can be integers. So if this n was a 0, I'd have 360 times 0 plus 40 would be 40. So that would be the original, if I just took the 0. If I took plus 1 and put it in, because that's the next positive integer, 360 times 1 is 360, plus 40 is 400. So that would be the next positive one. If I put a 2 in, I'd have 360 times 2, which is 720, plus 40, which is 760, which is my next positive one, and I can keep going. Now, the reason why it's a plus and not a plus minus is I have integers. So I just did the positive integers, but I could use negative 1. If I put negative 1 in here, I get 360 times negative 1, which is actually subtracting 360, correct? Which would be negative 320. Or I put in negative 2, would be subtracting 720, which would be negative 680, etc. Right?
If you wanted to express this as plus minus, would you put n as an element of the natural numbers or as the whole numbers?
Wholes, because you'd need that 0.
Okay.
Now, you could do that technically and say whole numbers, and you'd be correct, but any multiple choice or numeric response will be written as just a plus sign.
Yeah.
Okay.
Does it matter if you write I or Z for integers?
If you put the Z is actually accurate to university, and they'll accept it, but I is what they have in the textbook, so we do it. And I is what they'll show on the test. But Z is that. He's saying this. Actually, it looks like this. That's integers in university. Because an I means something totally different. But because we use the textbook and it says it's an I, they can use an I because they use it as the curriculum. But a Z is what you'll see in university. A double Z for integers or a double R for reals, etc. But we've seen Zs on the diploma in written response. They have to accept it because it's in an actual math textbook that it shows that Z, it means integers. Yeah. All right. So if I wanted to list coterminals, I could go 40 degrees plus 360. And I would get 400. Or I could go 40 minus 360. And I would get negative 320. All of these terminate on the same arm and would actually have, all of them would have the exact same cosine sign values, wouldn't they? Because they terminate on the exact same coordinate on that outside of that unit circle. Same dot. 140. Now, I'm going to repeat myself 700 times because people don't listen to me and I walk around and I see people not doing this. Have you labeled your axes? If you're someone who still hasn't, like the people who revolt against me with fundamental counting principle and don't put the multiplication symbols. You need to label it. You're like, I think that's just a suggestion. It's not a suggestion. It is Mrs. Lepp telling you what you need to do. Need means has to happen. Yeah? Okay. Labels. All right. So we have 140. 140 is 40 shy of 180. That kind of looks like 145. No one is going to kill me on that. They will if I draw it at 170 though. So that's 140. That's aggressively there. Okay. Negative 240. We've already drawn, I believe. So we have to label. We have 0, negative 90, negative 180, negative 270, negative 360. Still the initial arm is on the x-axis, still rotates around 0, 0, and 240 is 30 shy of 270, so it's like here, and we draw our arrow towards it. Then 340. It's positive, so I go 0, 90, 180, 270, 360, 20 degrees shy of 60, that might be 10, but, 340. Okay, we're going to flip over. Radians to degrees, degrees to radians. Dr. Pot. Degrees to radians, pi on top. Okay, so we're either multiplying by pi over 180 or we're multiplying by 180 over pi. And that's because, if you remember from your unit circle, this point on the unit circle was 0 or 360 or 2 pi. They're equally the same, right? So we could do 360 divided by 2 pi because it's a ratio, correct? They're the same. You can do ratios. We've always done ratios before. When you've done any conversions from like kilometers to, let's say, miles, you would do a ratio of kilometers to miles. What 1 to 1 kilometer would be to 1 mile or whatever. 1.6 kilometers is 1 mile. You do your conversion, right? So you can do this, but that would be silly to use that because I can reduce it. We agree? So hence where you get the 180 over pi. It's just from the ratio of 360 over 2 pi. It's the same thing. Okay? Now, when we want to convert degrees to radians, we want to get rid of the degree symbol. We agree? Like the same thing as when you do kilometers and miles. Honestly, you don't need to have these acronyms memorized. You can. It makes your life easier, sure. Go for it. Don't care. But what you need to know is I need to get units to cancel off. Just like if I was trying to get kilometers to miles, correct? I would line up the kilometers. If they were on the top, I'd line up my conversion ratio to have kilometers on the bottom so the kilometers would cancel off and I'd be left with miles. We agree? It's the same thing you do in physics when you want to get something to convert. You line up the same one with the top, same one with the bottom, the unit cancels off and you're left with the other unit. We agree? That's how you do conversion. Same thing here. So I'm either going to multiply by 180 over pi, 180 being the degree symbol, or I'm multiplying by pi over 180, 180 still being the degree symbol, pi being the radian measure. Make sense? So, if I want to convert from degrees to radians, I have 315. Now if you look here, degrees to radians, pi on top. That's what we can remember, Dr. Pot. Degrees to radians, pi on top. Or we can just use the method of conversion that we know in our head. Conversion means if I want to get rid of the degrees and I want to end up with radians, I need to line up the degree one with the bottom so the degree symbols would cancel and I'd be left with the radian unit. We agree? So 315, I would multiply by pi over 180 because the 180 is a degree. And now my degrees would cancel off, and what unit would I be left with? No units. And honestly, when you're left with no units, that's radians. So radians can either, you can write pi radians, you can write pi rads, or you can just write pi. If the actual angle has no units on it, it is a radian measure. That's why the degree symbol is so important. Because the degree symbol tells you it's a degree, and no symbol tells you it's a radian. So if you write 180 without the degree symbol, that's 180 radians, which is a huge amount. Okay? Because 2 pi, which is 6.28, is 360 degrees. So 180 radians is kind of crazy. Okay? So we just go 350 divided by 180, and what do we get? 315, sorry, divided by 180, and what do we get? And that would be in a rounded decimal, correct? It's just 1.75? Yeah. What is it in a fraction? Just give me that. What's 3/15? So if you put the pi into your calculator, to try this out. So go 3/15.
For sure it's not just 1.75.
Try this in your calculator. So go 3/15 times pi divided by 180. Put the whole thing in. Okay? And what do we get?
497.
Blah, 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 blah.
Yeah.
We need that when it's usually a numeric response. So when it's a numeric response, unless they go a pi over b, what's the value of ab? If they ask you to the nearest hundredth, you would have to type it in as 3/15 pi, well, it just switches when it wants to. 3/15 pi over 180. You would have to type that in and get a decimal. We agree? But if they say a pi over b, you need to reduce 3/15 over 180. Okay? Which you can take 15 out of all of them, and you get 7/4. Okay? So you have to put the 7/4 and then add the pi back. Because if you put the 7 pi over 4 or 3/15 pi over 4 and you press math enter enter, it's not turning into a fraction. Because pi will never turn into a fraction. Pi is a non-repeating, non-terminating decimal. So anytime you put a pi in, don't even press the math enter enter button. It's a waste of your time. Button pushing you'll never get back. So go 3/15 divided by 180. So 70 degrees, I need it to turn to radians. So I'm going to go pi over 180 degrees. The degree symbol will cancel. And now I'm left with 70 over 180 pi, technically. So if you type that one in, what does it reduce to? Yeah. You can also notice that you take a 0 out of each, right? Which would be 7 pi over 18. This is called exact values. What is not an exact value? A not exact value is a decimal. That just goes on for life. That's not exact. And some people say, well, I rounded it, so now it's exact. You rounded it. It was exact before you rounded it. The moment you rounded it, it's no longer exact. Okay? So if you're asked for an exact value, it is not a decimal. Unless it is like 3/4, and that is 0.75. That is actually an exact value. You didn't round it. 3/4 and 0.75 are the same thing. They're exactly correct. Okay? Another place that exact value pops up would happen in polynomials like we just did when I asked you for the solutions in exact values. That's when you use a quadratic formula. If you give me the decimals of the quadratic formula, you're not giving me the exact value. If you give me the reduced radical, you're giving me the exact value. Okay, now we want to convert from radians to degrees. So we want the radian to go away. So we're going to multiply by what? 180 degrees over pi. If you keep the pi symbol on the conversion, it'll help you out too, because I need the degree symbol to stay, right? So the pi's actually cancel off, and I'm left with what? Yeah. And I need to have a degree symbol, or it's a really negative large radian. Now the next one has negative 1.4 radians. I need the degrees to stay. So I know I'm going to have to multiply by 180 degrees over pi. So what's negative 1.4 times 180 divided by pi? And if you wanted to, you could write pi rads, right? These are the same things. Remember, you can write radians, you can write rads, or you can write nothing, and it's radians. Yeah. Is there a decimal with it?
What about the pi?
Oh, divided by pi.
Yeah.
So no. Divided by pi, it should be a decimal. Negative.
80.21409.
So what we should actually write when we do this, we should not write an equal sign. We should write a squiggly equal sign. This means approximately. The moment you round, you should really be writing an approximate symbol, because it's not equal to, it's an approximation. Yeah?
would it be valid to write negative 252 over pi degrees?
They'd accept that. It just depends on how they want it, right? If it's like they want the answer to the nearest hundredth, then you'd have to put the pi in. It's a numeric response. You're getting an answer. If they just want an answer and they don't say to the nearest whatever, you could go 252 degrees over pi. Totally fine. So does that make sense on the conversion? Okay. So we have this part of our unit circle. We're going to look at this quadrant. We agree? Okay. So this is 0 degrees. So if you look at your unit circle that I gave you, one of them has a degree symbol in the middle. There's a blank with a degree symbol in the middle. You'll put 0 there. And then there's another blank beside it. That's for radian measured. These are the only two measures that are actually the same in radians and degrees. So it's 0. Then we have what's next? 30. Then 45. Then 60. Then 90. How do we convert them to radians quickly? We just divide them by 180 and add a pi. Technically all you're doing. You're dividing by 180 and adding a pi. So 30 divided by 180 is what?
6.
Pi over 6. It's just 1 over 6. So the radian measure would be pi over 6. 45 divided by 180? Pi over 4. 60 divided by 180?
Pi over 3.
And then 90 divided by 180?
Over 2.
Pi over 2. Now the hard part, coming up with the coordinates, which are actually not the hard part. Because if you actually know that these are coordinates on the Cartesian plane, remember this is the Cartesian plane, it keeps going on, correct? This is just quadrant 1. Is that all this is? That's all it is. Now a lot of people don't know this, it's like mind-blowing when they get to grade 12. There's coordinates the whole way along here. Like these are all coordinates. There's a special one and some more coordinates. There's a coordinate for every degree. There's a coordinate on the unit circle for 72.3 degrees. There's a coordinate on the unit circle for 79. There's a coordinate on the unit circle for negative 315.2, right? Every single degree has a unit circle coordinate for it. So let's look here. This middle one, look at this one, the 45. Now, if you actually look at it, it is equal distance here as it is here. Like on yours, mine's not drawn perfectly. But if you look, the distance on the y is actually the same distance on the x axis. Like if you draw your coordinate, because we're trying to find an x value that it matches with and a y value that it matches with. That's why all the 45s are root 2 over 2. And in quadrant 1, what are my x and my y's? They're positive, correct? So it's root 2 over 2 and root 2 over 2. They're the same distance. Root 2 over 2 is like 0.707, blah, 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 blah. So they're both actually about approximately, remember your radius is 1. They're both approximately like 0.707. We agree? So that's why they're the same. Yes? Okay, let's look at the 30s. This is where people are like, I have to memorize. Is it root 3 over 2 first or a half? Or is it a half first or root 3? Why are you memorizing? It's on a Cartesian plane. Look at it. Look at that coordinate and see what happens to it. We're not memorizing, we're using knowledge. So if I go here, and I go here, does the y look like it's at a half or the x? Remembering that this, from here to the coordinate is 1. So does the x look like it's at a half, or does the y look like it's at a half? The y. So your y is a half. And what's your x? Root 3 over 2. And we just talked about root 3 over 2. Root 3 over 2 is 0.8660, correct? Does that look like an x of 0.8660 possibly on a distance of 1? Yeah. You should not mix them up. They're literally a coordinate on a Cartesian plane with a radius of 1, right? It should make sense. So if we look at this one, the y looks like it's maybe at 0.866. Let's pretend I actually drew this perfectly. I didn't. Yours, if you followed along, it actually will do it. And then this one looks like it's at where? Yeah, the x is at a half. The y is at 0.866. So memorization scares me because you can flip-flop. It shouldn't be memorized, it should be understood. It's just a coordinate, it's at a half and root through, like, right? Like, it should make sense. Where's this one at? A distance of, x of 1, and what's my y at? 0. Okay, what's this one at? My x is at 0, my y is at 1, because it's the radius of 1. We agree? Now, it just does the same thing the whole way around. Let's go here. I have coordinates on the outside of this unit circle. This one is 30 more, so it's at 120. Then 45 more, so 135. Then 60 more, so whoa, what am I doing? This is 180. This is 150. Remember, we have 30, 60, 90 reference angles. Now, what's 120 in radians? Yeah, it's just 120 divided by 180 with the pi. So 2 pi over 3. 135. 150. And 180. Pi. Now, this one's at the 45, which is perfectly the same distance to x, correct? It's at 0.707. But it's in quadrant 2. In quadrant 2, what are my x and y's? My x is negative, my y is positive. So I'm going to get negative root 2 over 2 and root 2 over 2. If I go up to this one, my x looks like it's at the half, and my y is at way up here, root 3 over 2, right? So I'm going to get negative a half and root 3 over 2. This one looks like the x, if I drew this properly, would be at a half, and then this would be at 0.866. So it's at negative root 3 over 2 and a half. And then what's this one at? On the Cartesian plane, if this is 0, 0. Do you see how there's no memorization needed other than like knowing the root 3 over 2s and the root 2 over 2s? Because that, like, someone had to tell you that that was the value, right? We had to figure it out by triangles last year. So I'm just telling you that it's root 3 over 2 and root 2 over 2 because last year you did the investigation of the triangles that showed it was root 3 over 2. Root 2 over 2. Then rinse and repeat. This one, they're both going to be negative. This one, they're both going to be positive. So that's why, you guys, whenever you have an angle that falls between 180 and 270, your coses and your sines are negative. Every cosine sine between 180 and 270 is going to be negative because every coordinate between negative 180 and 270 has a negative x and a negative y, cosine, 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 right? It should make sense to you. If your unit circle is just a sheer memorization technique, the trig is way harder. If you understand your unit circle, the trig is way better. So try and fill in the rest. And remember, you can always check your trig. You can always check your unit circle. I could go, okay, this is, I think it's for negative root 2 over 2 and negative root 2 over 2. Well, this is at 225. Well, I could go cos of 225 in degree mode, sine of 225 in degree mode, and I'm going to get negative 0.707, which is root 2 over 2. I can check these. Okay?